Hello, everybody. Today we have a pleasure to listen to a talk by Alberto Salvio. He will tell us about quadratic gravity in 1922. Please, Alberto, 1 hour.
Thank you very much. So thank you for inviting me to give a talk about quadratic gravity. So first of all, some introduction, quadratic curvature terms and their relevance. So quadratic gravity is an extension of Einstein general relativity that is obtained by adding quadratic in curvature terms to the Einstein-Hilbert Lagrangian that are local. And then they are written here. In principle, you can also add a term which is the square of the Riemann tensor. Here you have the square of the Ricci scalar and the square of the Ricci tensor. But that last contraction can be written as a combination of these two plus the total derivative, which is not going to change anything of what I'm going to say. So these two terms are unavoidably generated by matter loops, such as the one that is shown here, where the double wave lines are graviton lines, and this is, for example, a scalar. In that one loop, indeed, we have the renormalization group equations for alpha and beta. Here, these are obtained just neglecting the graviton loops, so considering just matter loops. So even if you just have matter fields that are, of course, necessary to have a realistic model, we have a running of alpha and beta. Here, NB and Fn and S are the numbers of vectors, Weyl fermions, and real scalars, phi A, and the psi AB are the non-minimal couplings between the scalars and the Ricci scalar. So as you can see, if you set alpha equal to 0 and beta equal to 0, then they are unavoidably generated at quantum level by the RGE. Now, so far we haven't considered the dynamics of gravity, but when you consider also the dynamics of gravity, it can be shown that quadratic gravity is actually a renormalizable theory. This was rigorously shown in the 70s by Stille. But there is an intuitive reason behind it. This is the fact that in the UV, neglected, the theory is the most general dimensionless one. And so you can absorb all types of divergences by redefining the couplings of these dimension 4 operators, that are the couplings that are dimensionless. Now, the general quadratic Lagrangian, quadratic gravity Lagrangian, includes the two terms I've shown you before that can be rewritten as a combination of R squared and W squared, where W squared is the squared of the Weyl tensor. And here I'm also redefining the couplings, introducing this F0 and F2 couplings. Then we have, in principle, also the Einstein-Hilbert piece plus a cosmological constant, that is the relevant Lagrangian for gravity at low energies. And then there is a matter piece Lm, which is, of course, needed. It is also possible to generate the mass scales dynamically. Dimensionful terms, such as the Planck mass, the electroweak scale, and the cosmological constant, so all particle masses as well, can be all dynamically generated through dimensional transmutation, some gravitational dimensional transmutation. But in this talk, I'm going to just take them as ad hoc parameters in the Lagrangian. I'm not going to discuss this possibility, mainly because of lack of time. Another motivation for considering quadratic gravity is the fact that the Higgs mass, mh, can be naturally much smaller than the Planck mass. Here I'm taking a tough definition of naturalness. A physical quantity is naturally small when setting it to 0 leads to an enhanced symmetry in the theory. And this ensures in particular that quantum corrections respect the smallness of the physical quantity. So let's argue why you can have a naturally small Higgs mass. So one can consistently compute the quantum corrections to the Higgs mass that I denote with this delta MH. And what is obtained is the fact that delta MH squared is proportional to the Planck mass squared. There is also a loop factor, 1 over 4 pi squared. And then you have the fourth power of Fi, where F2i is either 0 or 2, and F2 to the fourth power is a possibility. And another possibility is F0 to the fourth power times 1 plus 6 psi Higgs, where psi Higgs is the non-minimal coupling of the Higgs. So you have a contribution which is proportional to F2 to the fourth power, and another one that is proportional to F0 to the fourth power times this function of the non-minimal coupling. Now, if you require that the gravitational corrections to the Higgs mass is not much above the Higgs mass itself, the observed value of the Higgs mass itself, one obtains that F2 has to be not much bigger than 10 to the minus 8. This small value is actually natural, and it is indeed stable under radiative corrections, but it can also be shown to be natural in the definition naturalness that I've just reminded you. To show you that, let me notice that quadratic gravity is a realization of a more general idea, which is called softer gravity. So from the point of view of the Higgs mass, the problem of Einstein gravity is essentially the fact that gravitational interactions increase with energy. And so in Einstein gravity, they become bigger and bigger, and they go out of control around the Planck mass. The idea is to substitute this theory at very high energies with a softened version of it, where the increase of the gravitational coupling stops at some energy scale that I denote with this lambda g, which has to be for Higgs mass naturalness much below m Planck. Why? Because the gravitational contribution to the Higgs mass is given by this formula, where Gn is the Newton constant. And then, of course, you have at least one loop suppression, because this is a quantum effect. And by dimensional analysis, you have to insert also the appropriate power of lambda g. So requiring again that delta mh is not much bigger than mh gives an upper bound on lambda g, which turns out to be 10 to the 11 GeV. Now, this is natural because for such tiny couplings, the Higgs field acquires an approximate shift symmetry that protects MH. Of course, also the matter sector should respect this shift symmetry, but one can engineer a matter sector that satisfies this condition. However, still the cosmological constant, lambda, is not naturally equal to the observed value. And this remains a problem for quadratic gravity. Maybe one can use the entropic principle and address this entropically, but this requires the construction of a multiverse and the determination of a statistics over this multiverse to explain its value. This hasn't been done yet in quadratic gravity. So it remains a problem. There is also another issue of the theory, which is related to the so-called Ostrogradsky theorem. The Ostrogradsky theorem stated that classical Lagrangians that depend non-degenerately on the second derivatives of fields, of canonical coordinates, have Hamiltonians that are unbounded from below. This is an old theorem. And indeed, this applies to quadratic gravity, because looking at the degrees of freedom, expanding, for example, around the flat space-time, one finds the massless graviton, which mediates gravitational interactions at large distances. One finds also a scalar that I call omega, with square mass given by this formula. So it is proportional to F0 squared. But he also finds a massive spin 2 field with an abnormal sign kinetic term, which is a particular example of a ghost, a so-called ghost, and a square mass given by this formula. Now, this is a ghost, but I'm going to argue that the runaways that are suggested by the Ostrogarsky theorem can be avoided for the entire evolution of the universe. And also at the quantum level, one can and actually has to quantize the theory in a way that actually all the probabilities are positive and they sum up to 1. One thing I want to stress from the very beginning is that this abnormal graviton is associated with the Weil-square term, with this term here. So when F2 goes to infinity, the W square term disappears, of course, and the reason why it does so is because the mass of the spin 2 field goes to infinity. So you see that when the mass becomes very large compared to the energies of the phenomenon that you're studying, the ghost disappears, decouples. Okay. One can also study the Hamiltonians of the theory, expanding around the flat space-time, for example. One finds in the gravity sector, the graviton Hamiltonian, which is a sum over helicities plus minus 2 of something with the canonical coordinate capital Q, conjugate momentum P, with some momentum Q squared, space-time momentum Q squared. And also a Hamiltonian for the ghosts, with the sum over helicities plus minus 2 plus minus 1, 0, because it's a massive spin 2 particle, and also the mass appears here explicitly. You have some other conjugate momentum and canonical coordinate. The important thing here is this minus sign, which is the manifestation of the Ostrogarsky theorem. Now, to address this issue, we can, at the moment, only proceed perturbatively. There's no, as far as I know, non-perturbative definition of quadratic gravity, so this remains a problem. Of course, if you want to have a complete theory of quantum gravity, you have to formulate it non-perturbatively. But okay, this is the best we can do, so let's proceed perturbatively, and we split the metric into a classical background that solves the classical equations of motion and a quantum fluctuation h hat. And we proceed perturbatively in h hat. So the first step is analyzing the classical theory, where h hat is set to 0. There's no effect, quantum effect at all. And can we avoid these Ostrogarsky instabilities? I present now an argument that to argue that this is possible. Recall first that in the free field limit, we have the Hamiltonian of the ghost and nothing else for the ghost. In the limit in which the ghost is free, you have just this. But despite the minus sign, the couple ghost does not suffer from instabilities, because the sign cancels in the equation of motion. So, so basically, you have no problem in this case, as well known. On the other hand, effective field theory arguments tell us that at energies below M2, we should not find runaways, even if the abnormal graviton has an order 1 coupling, F2. So if you send M2 to a very, very large value, you obtain a decoupled theory. as we have seen. We obtain a theory in which the ghost is decoupled. So no bad things can happen in this case. Of course, if you have finite energies. In the intermediate case, then, when F2 is between 0 and 1, we must have intermediate energy thresholds above which you have these runaways. For F2 equal to 0, you have a decoupled ghosts, so the runaway energies, the threshold energies, is infinite. So you have a consistent theory up to infinite energy in principle. You can have a consistent theory up to infinite energy. So this energy threshold is infinite. For F2 of order 1, it is basically M2. Okay, so for intermediate values of F2, you have to have an intermediate energy threshold between M2 and infinity. So in the weak coupling case, when F2 is much smaller than 1, which is the case, by the way, compatible with Higgs naturalness, we must have an energy threshold which is much larger than M2. So this is a good news because it means we could see the effect of the abnormal graviton without runaways. This argument can be made precise in classical quadratic gravity. This is classical. It's just a classical argument. We are going to talk about quantum mechanics later on. And in the next slides, I will illustrate the argument for a classical quadratic gravity. And moreover, the whole cosmology can only involve energies below this threshold and avoid runaways, as I will discuss later on. So this is a scenario that can be called metastability in quadratic gravity. So quadratic gravity is not exactly stable at the classical level, but is some sort of metastable theory. Okay, so let's see the argument for quadratic gravity. First one separates the two derivative degrees of freedom, omega, the ordinary graviton and the abnormal graviton. How? One can perform a field redefinition, which is a rescaling of the metric, where f is some space-time function defined here, and that has to be positive in order for the field redefinition to be well-defined. You have to preserve the signature of the metric. And this field redefinition gives the action, an action of this form. So now we don't have anymore the R-squared term, but we have an Einstein frame action also for the matter piece. So you have some LME. This in particular contains an effective scalar, omega, the one that I mentioned before, that corresponds to the R-squared term in the Jordan frame, with Lagrangian given by this expression. You can do something similar for the abnormal graviton as well. You can consider an auxiliary field gamma mu nu and rewrite exactly the same action in terms of two derivative terms. Indeed, if you solve the equations of motion for a gamma mu nu and insert this equation of the solution of this equation of motion into this expression, you get precisely the previous S, where capital G mu nu is the usual Einstein tensor and gamma is the trace of gamma mu nu. One finds actually mixing h mu nu is not precisely the ordinary graviton, where h mu nu is the difference between G mu nu and the flat space-time metric at eta mu nu, but the ordinary graviton is actually a redefined field h bar mu nu, which is the sum of h mu nu and gamma mu nu. And then gamma mu nu represents the abnormal graviton. So what we are interested in is understanding the interactions of the abnormal graviton and the energy thresholds above which these runaways can be triggered. And this two-derivative formulation is good to understand these aspects. First, one can easily see that the interactions of the ghost are suppressed by F2. If you send F2 to 0, you have a decoupled ghost. Moreover, this term, which appears in the action, leads to mass and interaction terms of this schematic form. So you have a first term, which is a mass term. Phi2 represents basically the canonically normalized spin-2 fields, both the ordinary graviton and the abnormal graviton. And then you have a set, an infinite set of interaction terms. Now, we are interested in understanding when this interaction can possibly be of the same order as the mass term. When they are much smaller of the mass term, you have no problems. In the limit in which they go to 0, you have a decoupled ghost. So in that limit, you have no problem. So we are interested in the case in which they can be of the same order in order to avoid this situation. And they can be of the same order when phi2 is of order m Planck. You see, if you set phi2 equal to m Planck, they are all of the same order. If you do set phi2 equal to m Planck in the first term, you get m2 squared phi2 squared half. This is the mass term evaluated phi2 equal to m Planck, which gives you this expression that I call E2 to the fourth power, where E2 is M2 divided by the square root of F2, or equivalently this expression here. So now, for energies much smaller than this E2, the Ostrogradski instabilities are avoided. What does that mean? So these energies are, first of all, derivatives of spin-2 fields. We are treating the spin-2 sector now. And it is only the derivatives that can source these interaction terms. And we can apply this condition only to the boundaries, essentially, of our problem, of our differential problem, because the bulk values of the fields are dynamical. So we can only act on the boundaries. So this condition should be applied on the boundaries. Okay, so this was in the spin-2 sector. Analogously, one can show that the energy E in the matter sector must satisfy some condition in order to avoid these instabilities, which is different from the previous one, essentially because when you have some energy in the matter sector, to transfer this energy to the ghost and excite these interactions of the ghost, you need the coupling to the ghost. So if you introduce another coupling, you get a slightly different energy threshold, EM, which is the fourth root of F2, not the square root of F2 as before, times m Planck. And again, one has to impose it on the boundary conditions. For the matter sector, these energies are interpreted as field values times coupling constant, or field values times masses, or derivatives of fields, whatever appears in the Lagrangian dimension of energies. Okay, so this is not a conserved energy necessarily. This is the meaning of this E. Now, there is an interesting relation with chaotic inflation proposed by Linde that I'm going to talk about now. For a natural Higgs mass, F2 is expected to be of order 10 to the minus 8, as I said before, and M2 is of order 10 to the 10 GeV then. This gives you the following energy thresholds. E2 of order 10 to the minus 4 and Planck, and EM of order 10 to the minus 2 and Planck. These are very high energies compared to those accessible at accelerators. So it is clear that you cannot reach this energy at accelerators, and that inflation is the only stage of the universe that can provide us information about such high energy scales, at least observable information. So to proceed, in the case of inflation, note that the ghost is completely inactive in a FRW metric, because FRW metric is a conformally flat space-time, and so the W essentially vanishes. The contribution of W is zero. So only perturbations that break homogeneity and isotropy may destabilize the universe. And now it comes in this chaotic inflation theory that in which one interprets our universe as the result of an expansion of one of those patches, initial patches, where the energy scales of homogeneities that are called EI and anisotropies that are called EA were small enough. How small? Well, essentially small enough to neglect the inhomogeneous terms in the field equations for inflation. So EI has to be much smaller than this quantity, and EI and EA also have to be much smaller than H. Okay, so what is the relation with what I said before? The relation is that this chaotic theory so these conditions basically automatically ensure that the conditions that we have seen before to avoid the runaway solutions are satisfied. And this actually has been checked explicitly in many models of inflation, including the most popular one, like Starobinsky inflation, natural inflation, Higgs inflation, hilltop inflation, and many more. So we happen to live in one of those patches that were isotropic and homogeneous enough to satisfy the conditions that I showed you before to avoid the runaways. And in this theory, this chaotic inflation theory, the initial universe was composed by many patches, including some that were very much homogeneous and isotropic, arbitrary homogeneous isotropic, and others that were arbitrary inhomogeneous and anisotropic. So you can always find a patch that was homogeneous and anisotropic enough to avoid these runaways for the entire evolution of the patch. The other patches tend to collapse because of decay in general, because of Ostrogradsky instabilities, and there the life is impossible. So we must live in one of those patches that were initially homogeneous and isotropic enough. Okay, let's now go to the quantum physics, H hat. First of all, we ask whether a different quantization help. This actually is the case for classical Dirac theory, because a classical Dirac theory is a sick theory. You need to quantize it in order to solve the sickness. So we can hope that maybe something similar happened for gravitons. First of all, a renormalizability implies that the quantum Hamiltonian governing the quantum fluctuation is bounded from below. So this is a good news. However, the space of states must be endowed with an indefinite metric with respect to which position and momentum operators, let's say the field canonical coordinates and their momentum conjugate, are self-adjoint. Then we have to understand how to define probabilities consistently. If we just insert the indefinite metric in the Born rule, you get negative probabilities, which is a nonsense, unless you define what the negative probability is. But we are going to find that this is not correct, that you should not use the indefinite metric in the Born rule, but you should rather use another metric, which is instead positively defined. You must do that, as I will now argue. So first of all, I adopt a different definition of observable with respect to the textbook quantum mechanics treatment. An observable is any operator A with a complete set of eigenstates. So for any state in the Hilbert space, I can decompose, for any state psi, I can decompose along this basis. In quadratic gravity, in particular, one can show that the basic operators, the field canonical coordinate Q and the field conjugate momentum P, as well as the Hamiltonian, have a complete set of eigenstates at any order in perturbation theory. Then a first assumption, it's an axiom, which is present also in usual quantum mechanics, is to interpret this A as a state where the observable assumes certainly the value A. We call it the deterministic bound rule. If you want, this is a way in which we model quantum mechanics. Next, we reason as experimentalists would do. Experimentalists prepare a large number n of times the same state, so they consider a direct product of psi n times. So what we do is we model what the experimentalists do by considering the direct product of psi n times, which is essentially repeating the experiments n times. We also introduce a conventional overall factor nu to the n, where nu is given by this expression. If you decompose with this expansion, you get this formula. Next, we define a frequency operator, Fa, which acts on the space where this capital psi lives and counts the number Na of times there is this value A, the particular value on the observable, in the state, the big state A1, An. So Fa is defined in this Hilbert space, is this big Hilbert space, as operator that on this basis gives you an A over n times the same element of the basis. Now one can show that in the limit in which you perform infinite number of experiments, Fa on this big state, psi n, the generic state, goes to precisely the Born rule, Ba, times the same state. But the Born rule is defined here, the usual Born rule. Notice that this is positive, and Ba, if you sum it over A, you get 1. This convergence is in the sense that all coefficients in the basis A1, An converge to the same quantities. So as a result, the state goes, for n going to infinity, to an eigenstate of the frequency operator. So this Ba must be interpreted as the probabilities itself. So the probabilities are positive and they sum up to 1. So to compute this, you should not use indefinite metric because it would give negative probabilities, which is not the correct answer. And to see what norm you should use instead, let's define a norm operator, Pa, in this way, where A and A prime are elements of the basis, and delta A prime is a Kronecker delta. And also for any pair of states, psi1, psi2, we denote the indefinite metric with the symbol. This definition provides a positive metric, a norm, defined in this way. Indeed, if you set psi1 equal to psi2, you get a positive value for psi1A. So this is a positive metric. Now, if you express this Born rule in terms of this norm, you get the usual expression. So this is the norm that must be used to compute probabilities. And this is the one that I'm going to use later on. Another ingredient that is needed to quantize the theory consistently is the so-called Dirac-Pauli quantization. Notice that A is normal because it admits a full state set of orthonormal states with respect to this norm. So A can be decomposed in the sum of an Hermitian plus an anti-Hermitian operator with respect to the same norm that commute with each other. So we can always restrict yourself to operators, observables that have either a purely real or a purely imaginary spectrum. And in the case of pure imaginary spectrum, you can interpret the observable quantities as the imaginary part of the complex number, so as a real number. Now, in quadratic gravity, there are also observables that realize the second possibility, that must realize actually the second possibility. In particular, the canonical coordinates Q and P with standard commutation relations of the abnormal graviton. Indeed, this is the only option which allows a Hamiltonian of this form with a minus sign, like the one of the ghost, to have a spectrum bounded from below and normalizable eigenfunctions at the same time. Okay. So another important aspect of a theory of quantum gravity is UV completeness. So what happens above M Planck in this theory? So this theory actually cannot be phenomenologically viable and asymptotically free at the same time. This can be obtained by looking in particular at the RGE of F0 squared, which is this one. And one obtains that F0 squared, this coupling, is asymptotically free only for F0 squared negative. But F0 squared negative is a problem because omega becomes a tachyon. You can also visualize it by looking at the potential of omega. If you plot it for F0 squared positive, varying, for example, the cosmological constant lambda, you find a vacuum. While if you plot it for F0 squared negative, you don't find a vacuum. And this remains true also if you add an arbitrary number of other scalar fields. In this case, asymptotic safety can save us. Indeed, it can be shown that for F0 going to infinity, in the infinite energy limit, F0 does not hit any Landau pole, provided that two conditions hold. One is that all scalars have asymptotically value-invariant couplings, where for value-invariant couplings, in particular, one means that psi AB has to equal to minus delta AB sixth. And also all other couplings approach fixed points. In this case, quadratic gravity can flow to a value-invariant theory, also known as conformal gravity, at infinite energy. At low energy, the theory will not be conformal gravity anymore. One possibility is the quasi-conformal scenario, in which you have Einstein gravity at low energies for energies below M2, in which 1 plus 6 psi is very small, and also quasi-conformal gravity for energy above M2, where again 1 plus 6 psi is very small, and also F0 is very large, because you have to be close to the conformal value. So when F0 goes to infinity, the R squared term disappears and you have an approximate conformal theory. And also F2 small. In this case, what I call lambda G is equal to M2. Otherwise, you have another scenario which has not been explored so far, which is a case in which both F0 to the minus 1 and 1 plus 6 psi are large at observable energies, at low energies. In this case, lambda G is equal to the maximum between M0 and M2. There's also another interesting fact, the fact that since quadratic gravity flows to conformal gravity in the UV and the FRW metric is conformally flat, the initial time cosmological singularity of GR can be avoided. So the bottom line of this slide is that the way quadratic gravity is UV complete is a particular case of asymptotic safety. There is essentially a UV fixed point for all couplings. Let's now go to the inflationary observables. We distinguish between two cases. One is M2 larger than H, and the other one is M2 smaller than H. For M2 larger than H, you have no differences compared to GR. This is the case in which M2 is large compared to the accessible energies, that in the case of inflation is the Hubble rate H. So again, when M2 is large, the ghost is decoupled. For M2 smaller than H, you have two effects. One is that the tensor to scalar ratio gets suppressed compared to the Einstein case, Re, is suppressed by this factor. And this is interesting because models that are excluded for a large Re, such as quadratic inflation with a scalar field that features a potential equal to a mass term, become viable in this case. This is excluded in Einstein gravity. And the second point is that there is an isocurvature mode which fulfills the observation bounds corresponding to the scalar component of the abnormal graviton. So the reason behind this fact is that PR, the curvature power spectrum, is not changed by the abnormal graviton, at least in the slow-lobe approximation. So NS, the spectral index of the curvature perturbations, is not changed either. While the tensor power spectrum is changed by the same factor that changes R, the tensor power spectrum, and also, third point, there is a curvature power spectrum, PB, is the same as the tensor power spectrum in Einstein gravity, except that it's smaller by a factor roughly 1/5. This is a complete expression. And also the correlation power spectrum between the curvature and B is highly suppressed. So in this plot, I show the bounds on this isocurvature mode. Here, Q1 and Q2 are two reference values for the momentum typically used by the Planck collaboration. And the strongest constraints from Planck have been used here. Here, I plot PB at Q1 and PB at Q2. And the central line, the dashed line, is the value for a single field model. But I allow this relation to break down because it can be broken in multi-field inflationary models. In particular, the upper solid brown line corresponds to epsilon going to 0, where epsilon is the slow-roll parameter, first slow-roll parameter. And the lower solid brown line corresponds to epsilon of order 10 to the minus 2. Now, the thick dashed red line, this one, corresponds to the 1 sigma constraint from the Planck collaboration. And the other one, red dashed line, the 2 sigma bound. So you can see for RE up to roughly 0.1, you still have a perfectly allowed theory, although this is excluded in Einstein gravity. Okay, so let's mention some specific inflationary scenarios. One can be scalar inflation. This is pretty natural because you have an R-squared term in the action. So we can implement scalar inflation proposed by Starobinsky a long time ago. This was actually the first model of inflation. This requires, however, F0 10 to the minus 5, of order 10 to the minus 5. So we would be far away from what was called the quasi-conformal scenario. So you have to use the other scenario. But the quasi-conformal scenario is easier to investigate. We have already done it. So it is interesting to ask whether there's an inflaton candidate in the quasi-conformal scenario as well, where 1 over F0 is close to 0, and also psi AB is close to this conformal value. And two options were found. One is the case in which the inflaton is a fundamental scalar with a quasi-conformal non-minimal coupling, so the Ricci scalar. In this case, the field excursion must not exceed the Planck mass by far, and an explicit example was found in the context of hilltop inflation. The other example is the case in which the inflaton is a pseudo-Goulston boson, the so-called natural inflation case, proposed by these authors in the 1990s. In this case, one can elegantly obtain a UV completion within some asymptotically free QCD-like theory. QCD-like because the confinement scale of this theory should be close to almost the Planck mass. So this is an advantage with respect to the first case where no UV completion was found so far. In the natural inflation case, the potential, the n, is chosen to be this, where now lambda is not a cosmological constant, some energy scale different from the cosmological constant, and f is some other energy scale. And it was found that the conditions to avoid the Ostrogransky instabilities are satisfied in all these cases. Now, so we have mentioned natural inflation, we have mentioned Starobinsky inflation. Let's analyze both now. And we allow also for a mixed case in which you have a two-field inflationary model where both the pseudo-Nambu-Boston boson and the scalaron can be active. We can go to the pure natural inflation case and to the pure scalar inflation case by taking this parameter to be respectively small or large. This can be easily understood by looking at the action. These are the plots of h and lambda as a function of this parameters, key parameter rho. And as you can see, h is close to the bound by Planck, provided in 2018, for a very small value of rho, but still allowed. For example, for n equal to 60 is below the bound, and then it goes much below. This is for f, for a particular value of f equal to 8 and Planck. And here on the right, I give you the corresponding values for lambda as a function of rho that is obtained by requiring PR to match the observed value. But another important parameter is f. So we are also interested in varying f. This plot is obtained by fixing rho and varying f. And in this case, we find a curve which is much below the Planck bound because we are setting rho equal to a sizable value. And this is the corresponding plot for lambda. Now, the most interesting thing to see is are the curves, the predictions of the theory in the NS R plane compared to the current bounds provided by Planck, and also more recently by the Bicep-Keck collaboration that released a paper at the end of 2021. So this is the result. So let's first focus on the case M2 much bigger than H, where the ghost is the couple. So in this case, we vary rho and fix f equal to this value. So we see that when rho goes to 0, so in this case you recover natural inflation, the theory is excluded. But when rho becomes already close to 1, but even before, for 0.5 is fine, for example, you have predictions that are in good agreement with data. And here we are fixing rho and varying f. And we found again good agreement if you take f to be sizable enough. So essentially f has to be transplanckian. Otherwise you go a little bit out from the bounds. Still acceptable, but this is always for f transplanckian. So it has to be transplanckian. I think if you go below the Planck mass, this goes out. So you can have compatibility with observations, even for the couple ghost, if you use the R-squared term. But you can have compatibility also without the R-squared term, but using the ghost. For example, in this case, M2 is not much bigger than H. And even if you set rho equal to 0, you find in this case good compatibility. This is by fixing f, and this is by varying f and fixing rho. Again, you can find compatibility. Okay, good. So another topic I want to talk about.
Do you get any lower bound on M2 from cosmology?
Lower bound on M2 from cosmology.
Yeah, or it can be as small as you wish in cosmology. Forgetting about solar system experiments on just about cosmology.
So yes, I don't get any at the moment. So if M2 is So if M2 is small enough, then this object goes to, the denominator goes to infinity, so R goes to 0.
Which is still fine, right?
Which is still fine, yes, which is still fine, yeah.
Okay, let's see. Okay, thanks.
Good, so let's go to the last topic I want to talk about, that are ultra-compact objects, for example, black holes. So interesting fact is that there must be a linear description of some ultra-compact objects in this theory, because gravity is softened for energies above lambda g, and so for length scale below 1/lambda g. So a linearization mechanism should take place for these scales. So light enough objects can be described by the linearized theory when there's partial radius RH, given by this formula, m is the mass of the object, satisfies this condition. So in this case, we can actually describe analytically ultra-compact objects, even if the mass to radius ratio is higher than for a Schwarzschild black hole. On the other hand, it's interesting to mention that when this condition is not satisfied, so for RH roughly bigger than 1/lambda g, nonlinear horizon-less solutions are also found that mimic black holes. This was found by Haldon and Wren already in 2016. And there are also more recent papers with some generalization. This is interesting because it means that the theory also predicts, at least in the cases described by these authors, horizonless solutions, even for astrophysical black holes, when RH is, of course, much bigger than 1/lambda g. But I think this was already discussed by Bob in his previous talk. So I will actually focus here on the linearization mechanism. To understand this mechanism, let's first consider a point-like mass. So the energy momentum tensor has this form where m is the mass of the object. And in this case, of course, the trace of the energy momentum tensor is not 0. And so we are not in the quasi-conformal case, and lambda g then has to be equal to the maximum between 0 and 2. So the reason why the linearization mechanism occurs in this case is very simple. If you look at the Newtonian potential generated by the source, you can find an upper bound on this Newtonian potential, which is given here by doing some manipulations. Now we see that for RH much less than the minimum of 1/m0 and 1/m2, so the inverse of the maximum over m0 and 2, the potential at the end should be small, and the horizon does not form even for an ultra-compact object. Now, this is a singular source, it's a delta function, and generates a singular potential. Well, the potential is actually finite, but there is a singularity in the curvature in this case. So one can wonder, okay, maybe the theory is sick because there is a singularity, but I would rather argue that this is the fault of the source rather than the theory, because the same 1/r singularity also occurs in even an asymptotically free Yang-Mills theory if you put a delta function source. For example, if you put the source along the time component of the current, there's always a Coulomb-like solution which goes 1/r, even if you have a Yang-Mills theory which is perfectly well defined in UV. So this is not, I think, a manifestation of the sickness of the theory, but nevertheless, we can also consider general sources and spacetimes that can be regular everywhere. We consider the general ansatz written here, where rho p and p orthogonal are functions of the radial coordinate r. And defining delta A and delta B as the difference of those metric functions A and B with respect to 1, we found the solutions written here, where these functions V and U are obtained through rho and p with these formulas. You can give an example: a ball of constant density ρi, radius r, and mass m. The solutions are written here. And these plots are provided for these specific values of the parameters. In particular, RH is bigger than R. So in GR, this would be a black hole. In the first plot, I show you the values of A and B in the linear analysis. And this dashed brown line is the Schwarzschild solutions. You can see for R much bigger than 1/0, we approach the Schwarzschild solution, but for values much smaller than 1/0, you have a quantity which is close to 1. And you have a regular pressure, which is positive, as should be, and regular curvature invariance, Ricci scale squared, Ricci tensor squared, and bi squared. We also check the validity of the realization mechanism numerically by comparing the linear solution for A and B with the non-linear solution for A and B when the linearization mechanism should hold, and we found good agreement. And also, we checked that the Ostrogradsky stability and metastability are satisfied. The conditions to obtain the metastability in quadratic gravity are satisfied. Let's illustrate why. So we start from this basically definition of RH, which can be written also in this term, because rho bar is the average energy density. Now, if you use RH much less than 1/lambda g, and R less than RH, which the first condition would correspond to having a realization mechanism, and the second one to having a black hole in Einstein gravity, you get that rho bar can be written in this term and is much bigger than this quantity by doing simple algebraic steps. From what we said before, the Ostrogradsky instabilities, on the other hand, are avoided for energy densities much less than m2 m Planck to the third power. In these conditions, this one, to avoid the Ostrogradsky instabilities, and this one, to have realization mechanism and black hole in Einstein gravity, can be both satisfied for m2 much less than this quantity, which can be satisfied. In some cases cannot be satisfied, but in many cases can be satisfied for values of m2 that correspond to a natural Higgs mass. So it is possible to have this metastability. There is also another plus. So this theory says that there are no macroscopic black holes, where macroscopic means RH much less than 1/lambda g. And this is good for the Higgs vacuum in the standard model, because it has been argued that a black hole with RH less than 1/h max, where h max is the value of the Higgs field for which the effective Higgs potential acquires its maximum, is very dangerous for the standard model, as it can induce electroweak vacuum decay. And this type of black holes can be avoided in this case by setting lambda g to the corresponding quantity, essentially of order 1/h max. Sorry, 1/lambda g of order 1/h max. Also, the ultracompact objects are stable. If they are stable, they can be dark matter. But I don't have time now to discuss this topic. So let's go to the conclusions. Quadratic gravity can be a UV complete gravity theory along the lines of the asymptotic safety, in the sense that you can have a fixed point. The classical runaway solutions can be avoided even at energies exceeding the ghost mass. And we have also discussed how runaways occurring above these energy thresholds in patches that are different from ours can explain homogeneity and isotropy in our patch. So we must leave in one of those patches that are enough isotropic and enough homogeneous to avoid these runaways. Moreover, interpreting probabilities as emergent from repeated experiments leads us to a way of quantizing the theory where all probabilities are positive and they sum up to 1. And we don't have a choice. We cannot do something else. We cannot use indefinite metric directly in the Born rule. Also for F2 of order 10 to the minus 8, which is the maximum value compatible with Higgs mass natural mass, quadratic gravity leads to testable predictions for the inflationary observables. It can suppress the value of R. In many models of inflation, this is true, and including the most popular ones, and render viable many models that are ruled out in Einstein gravity. For example, natural inflation without the R-squared term. Moreover, ultra-compact objects are eventually horizonless. Eventually means for RH much less than 1 over lambda g, and are compatible with Higgs mass metastability, and do not evaporate eventually because eventually don't have an horizon, and can account for dark matter. What is still remains a problem to me is to find a non-perturbative formulation of this theory. So we have proceeded perturbatively, first at the classical level, and then including h mu nu perturbatively. We would like to have, we must have actually a non-perturbative formulation of this theory, where everything is generated without expanding in powers of the quantum fluctuation. The cosmological constant also is not naturally equal to the observed value in the definition of naturalness we used. Maybe one can only use the entropic principle and the multiverse to explain its value, but of course this would imply also fixing some statistics in the multiverse. We don't have any clue, at least I don't have any clue how to fix these statistics at the moment. So this remains a big problem. Thank you very much for your attention.
Thank you very much. Thank you very much for your very interesting and very instructive talk. Question, please.
Yeah, I have a couple of questions, if I can start.
Yes, Luca, please.
Yeah, so the first is about the quantization prescription that you use. So, of course, you discussed first like some classical properties of quadratic gravity and then quantum properties in your talk. So my first question is, for instance, let's suppose you start from your quantum theory that you quantize in the way you showed. If from your quantum theory you take some classical limit, would you see at the classical level some remnant of your quantization prescription?
Well, I think that this would imply knowing the non-perturbative formulation of the theory. So what I'm doing is really separating the classical background from the quantum fluctuations. So if you have a complete non-perturbative formulation, then the classical background should emerge as a limit of the quantum theory. But this I cannot do with this approach. So this remains an open problem that I think can only be solved once you have a non-perturbative formulation of the theory.
Yeah, because I mean, recently, as you know, there have been several approaches with different type of prescriptions, say, to quantize the theory. So my question was more like, can we really discriminate among these prescriptions, like somehow?
Well, I understand the question. So, I know some prescriptions. So, for example, I know the one I haven't understood completely, but I know the one by Anselmi. So I was curious to see if the two theories differ somehow. And the only predictions that can be tested observationally are those in inflation. Okay, so I want to see whether these inflationary predictions found together with some other authors agree with mine. And actually, they do. In the range of validity of their prescription, there is a range of validity in which what he calls the Fakian projection can hold. And if you impose that condition, you get precisely the same predictions.
Okay. So somehow this is not very good, right? You cannot discriminate. I don't know. It's
well, at least with that approach. Oh, I know also the one by John Donoghue, which is, well, basically the Lewick approach. And in that case, also, I think I found agreement, at least if you do tree-level calculations. For the loop calculations, my prescription gives a formula which is quite complicated. So as far I haven't managed to implement it in loops. But at the tree level, it precisely gives what John is doing.
I see.
So also in that case, I cannot discriminate. So it reduces to know things.
I've just one last question. So, for instance, let's suppose we apply this theory to study gravitational waves from some astrophysical object, I don't know, binary image or whatever. Now, of course, yeah, you have more propagating degrees of freedom, among which this abnormal graviton that has a mass. So, of course, this abnormal graviton will also contribute to some propagating wave, some massive graviton, or I don't know, some type of wave. Let's not call it just gravitational wave, not confuse it with massless graviton. And of course, in principle, you should see something because anyway, they couple to matter. So you should see from some matter distribution also this type of wave to be generated. Now, of course, if the mass is very large, you would see something maybe, I mean, some wave which doesn't go at the speed of light. Okay. And maybe you could see already in some, maybe with current observation of gravitational waves, we could already put some constraint on the mass of the abnormal graviton. So I was wondering whether if you know, whether to be consistent with, if you can say anything, let's say from gravitational wave experiment on the mass M2 of this abnormal graviton, if it can be large enough or must be quite small.
Okay, so I was initially interested in understanding this topic, but then I realized that I think there's no situation where you have sizable corrections to gravitational waves in the Einstein-Hilbert theory, because you have the application of the running of the gravitational couplings that I show you in one of the first slides. So you remember that in software gravity you have this behavior. So basically, if you are below lambda g, you just have Einstein gravity. If you are above lambda g, the couplings goes to 0. So gravitational waves tend to be suppressed in this regime. So either it mimics very well Einstein gravity, or else it is suppressed. So yeah, there is a modification, but it tends not to be visible. When there is a modification, it tends not to be visible. When it is visible, it is very similar to Einstein gravity. So maybe you should look precisely at the intermediate regime, but this is quite narrow. And
so you think that you can put any constraint on M2?
I think that the constraints would be very weak because of this reason.
Because I mean, the coupling between the matter and the spin 2, abnormal spin 2, would be very suppressed, basically. That's
yeah.
Okay. Okay, I will think more about it, but thank you.
Well, even with gravitons, even with normal gravitons, So this is the full gravitational interactions.
Mhm.
So this is the reason why R, the tensor to scalar ratio, gets suppressed. That is the ratio of the tensor power spectrum of the graviton, the normal graviton.
Mhm. Yeah, sure.
By the one of the curvature. It is suppressed, so it suppresses also the usual graviton interactions at large energies. Small energies it doesn't.
Mhm. Okay, thank you.
Okay, I see a next question from Philip. Philip, please ask your question.
Yes, but first of all, Alberto, hello, and thank you for the presentation. I only have some quick comments, not questions.
Okay.
Some of the things you've been doing are very similar to what Carl Bender and I were doing, in as much as you change the inner product in order to get positive probability.
Yeah. I missed to say that from that point of view, changing the inner product is indeed very similar to what you did. Yes.
And the other thing, by the way, that we also did was we had some of the operators not be Hermitian, which you also discussed. But I wanted to comment. You mentioned Gerard de Hoof's sort of rule of thumb. A quantity is naturally small if, when you set it to 0, you get an enhanced symmetry.
Well, this is just my definition. Is not more than that. So if you take another definition, things will change. Okay,
well, let me pursue it. So what I've been doing is asking, well, is there a limit in which the cosmological constant is 0? And the answer is if you have the conformal gravity, but without the second order. And what I've traced, the origin of the cosmological constant problem is because you have the second order and the fourth order. And if you just have the fourth order, then you have an additional symmetry which can control it. And that's what I've been discussing. Anyway, that's the comment.
You mean conformal Wall invariance, you mean?
Yes.
Well,
pure W squared.
Yeah, okay. So I have a problem with that. So first of all, we found that if you put matter fields, Wall invariance is always broken at low energies. So there's no way you can have a Wall invariant theory at all energies and at the same time have a viable theory. People are having the matter fields.
Yeah, it can only be the mass scales can only be coming through the vacuum. The conformal symmetry has to be broken spontaneously. It's not just an approximate symmetry at high energies. It must be an exact symmetry of the equations of motion, but it must be broken in the vacuum.
Oh, well, if it is spontaneously broken, then also the cosmological constant will be generated.
Yes, that's correct.
It has to be spontaneously broken in order to generate the masses of particles we know.
Yes.
So now if you construct the effective field theory below the scale of spontaneous symmetry breaking, the theory will look like non-conformal. And if you compute the cosmological constant, you will get an enormous value, enormous natural value.
Okay, well, I mean, the answer to that is, I mean, I've done all that. I mean, I'm aware of that issue. The thing that will control the cosmological constant is quantum gravity. You see, we've always looked at the cosmological constant as a problem in the matter sector, but there's an interplay between the matter and the gravity sector, and that's, in the end, is what controls the cosmological constant, and it leads you to a very constrained value. I talked about this at the last meeting, but I don't want to, I didn't want to give a whole speech. I just wanted to make the comments.
Okay, let's see.
Okay, I see a next question from Sergei Vernov. Sergei, please ask your question.
Thank you for your talk. I want you work only in Einstein frame, but why are you sure that your function f is always positive? Maybe during evolutions it changed the sign.
What is positive? Which
The function f, what when you make conformal transformation of the metric,
Oh,
you use
yes.
some function f. Why you are sure that it is always positive?
No, I'm not sure. I'm imposing to be. So what I'm saying is that if it is positive, then you can do this field redefinition. This was to show how to. This was basically an easier example in which you can get rid of higher derivative terms by adding an extra degree of freedom. Before going to the case of the abnormal graviton. So in this example, I had to impose f to be positive, which I'm not sure it holds. You're right. In order for this field redefinition to be well defined. Indeed, I actually found cases where this is not satisfied. So I completely agree with you. This is you should read it like this. You do this if f is positive.
Okay. So, why you need Einstein frame? Why you cannot do the same procedure in the Jordan frame?
I think you can do that as well. This again, this was an easier example in which you can trade a higher derivative term with some extra degree of freedom, some extra field. It was an example. You can also directly go to the abnormal graviton case and remaining in the Jordan frame. Actually, I did some numerical calculation directly in the Jordan frame as well. So I don't need to go to the Einstein frame.
Thank you.
Okay. More questions, please? I see. If there is no more questions, let's thank the speaker again. Thank you very much, Alberto, for your talk. And please don't forget to send us your transparencies, okay?
Okay, good. I will.
Okay. Thank you very much.
Thank you.
Thank you very much,
Thank you,
Alberto.
Alberto. Thank you very much.
Thanks.
Okay, everybody, bye-bye.
Bye-bye.
Everybody, bye-bye.
Bye, Philip.
Bye.
Bye.
Hi, Richard. Hello again.
Yeah, bye-bye.
Good to see you. Good to see
Good to see
everybody.
you.
Yes, bye-bye. Bye-bye.
Yeah. I liked your presentation very much.
Oh, thank you.
Thanks a lot.
Mhm.
There we go.
Okay. Thank you very much, Alberto.
Thank you.